The ocean remains the last great reservoir of unobserved phenomena on Earth, a realm in which human understanding extends only through narrow beams of light and brief technological intrusions. Satellites trace weather systems, coastal currents, and surface temperatures with accuracy, yet none of these tools penetrate meaningfully into the profound layers beneath. The deep remains unmapped not because of disinterest, but because of physical limitations that no amount of engineering can fully overcome. Pressure collapses steel, darkness consumes instrumentation. Chemical gradients distort readings. The vastness itself overwhelms the capacity for systematic observation. For this reason, many of the most significant marine discoveries have been unintentional. A seismic drone capturing a faint outline, a volcanic eruption revealing something drifting just beyond visibility, a damaged cable snapping under the weight of something alive. Such encounters reveal not well understood species, but glimpses of organisms adapted to a world beyond the reach of human senses. The recording captured by fishermen on the North Pacific continental slope belongs to this tradition of accidental discovery, except it introduced a category of organism that had been theorized but never observed. The fishermen who captured the footage did not intend to participate in scientific inquiry. Their camera system had been installed to monitor equipment, not life. Positioned beneath their vessel, it faced downward toward the trawl net, illuminating only a narrow cone of water and the silt stirred by the vessel's movement. The environment itself was ordinary: particulate drift, bioluminescent specks, slow movement of suspended organisms, and scattered shadows produced by the vessel's lights. Nothing suggested the presence of anything unusual. The anomaly began with a change in particle behavior. Suspended detritus moved not according to current, but according to displacement from below. The movement was too smooth and too coherent to be turbulence. Instead, particles bent inward as if drawn toward an unseen mass. The water folded around something immense, a presence so large that only its effect could be observed initially. Moments later, the camera caught contact with the organism itself. A dark surface entered the edge of the frame, smooth and continuous, lacking scales or the pattern typical of fish or whales. It moved with rhythmic pulsations, each pulse expanding and contracting across a surface too close to fully observe. The camera's infrared system attempted compensation, revealing faint gradients of internal motion waves of fluid shifting through channels beneath an elastic outer layer. These waves traveled slowly, with the deliberate cadence expected of deep-sea metabolisms, where energy is scarce and efficiency determines survival. The organism's movements did not align with any known megafauna. Whales move with muscular propulsion and visible skeletal structure. Squid reveal arms, fins, or jet pulses. Sharks glide with predictable fin geometry, but this organism displayed none of these features. Its movement resembled the slow undulation of deep pelagic cnidarians, yet stretched to a scale far beyond anything documented. The fishermen did not recognize the importance of the footage at first. Later review revealed what they initially dismissed as a shadow was an organism so large that the camera struggled to resolve its boundaries. Only when marine scientists isolated still frames and enhanced contrast did the full extent of the anomaly become clear. The organism's visible section alone exceeded 10 meters, yet analysis suggested this represented only a fraction of its total form. Several curving lines visible deeper in the frame indicated additional structures moving in parallel. The organism exhibited a property that immediately caught the attention of oceanographers. It produced no detectable noise. Hydrophones recorded nothing. Even the displacement of water was muted. Large marine animals generally create acoustic signatures detectable kilometers away, yet this being moved with complete silence. Such silence implies a biological adaptation intended for survival in environments where sound travels with extraordinary efficiency. Silence is an evolutionary advantage in the deep, where even the faintest noise can reveal location. This characteristic reinforced the conclusion that the organism originated from depths far beyond the fisherman's typical working zone. It was out of place, not because of aggression or behavior, but because of vertical displacement. The continental slope acts as a transition between shallow and tidal ecosystems. When animals adapted to extreme pressure rise unexpectedly, Their physiology often appears altered or distorted due to stress, yet this organism moved naturally. No signs of decompression stress appeared in the footage. This indicated one of two possibilities. Either it ascended very slowly over time, adjusting gradually, or it possessed physiological properties that prevented pressure shock. Further analysis revealed additional anomalies. Chemical readings taken days later from the same region indicated dissolved oxygen fluctuations inconsistent with normal conditions. Trace elements suggested recent tectonic activity. These factors may have pushed organisms from deeper trenches upward as geological forces temporarily disturbed their habitats. Alternatively, the organism may have followed prey displaced by these shifts. When scientists attempted to contextualize the footage with existing biological models, they found no suitable classification. The visible features suggested a gelatinous macroorganism evolved in high-pressure environments. Its internal waves implied distributed vascular channels rather than centralized organs. This distributed physiology is common among deep-sea colonial organisms, but never at such scale. Archived sonar scans from previous years revealed similar distortions, long arcs, consistent with soft bodies moving slowly across midwater zones. These distortions had been dismissed as equipment anomalies due to their absence of clear boundaries. However, with the new video as reference, these anomalies were recognized as consistent with organisms of extreme size and fluid morphology. The footage also revealed a phenomenon previously unconnected with biology: particulate clustering. As the organism moved beneath the vessel, suspended particles aggregated into swirling formations shaped by the entity's displacement field. This type of particulate behavior had been observed in rare hydrodynamic simulations involving flexible bodies of enormous width moving at extremely low speed. The organism appeared to manipulate water not through active propulsion but through slow deformation of its structure, producing minimal turbulence. This method of locomotion had not been observed in any known marine species. It aligned with theoretical predictions of life adapted to deep zones where energy conservation is paramount and rapid movement is unnecessary. Deep-sea organisms often favor metabolic slow cycles, but none had been observed at this level of scale. The fisherman's regret emerged not from fear of the organism itself, but from the consequences that followed. Marine authorities seized the footage for analysis, and the fisherman's vessel became the focus of media speculation. Reports exaggerated the encounter, attributing danger or aggression where none existed. Public fascination turned into invasive interest, drawing criticism and unwanted attention toward individuals who had simply captured accidental data. Their regrets stemmed from the disruption of their privacy and the weight of a discovery they neither sought nor wished to claim. To scientists, however, the recording marked a pivotal moment. For decades, indirect evidence had suggested the existence of macroscale gelatinous organisms inhabiting the depths between trenches. Their presence had been inferred through chemical anomalies, drifting shadows, and unexplained disruptions in deep currents, but visual confirmation had remained elusive. The footage captured not merely an organism, but a category of life. A category defined by slow movement, vast scale, and biological silence. A category evolved for survival in conditions radically different from the upper ocean's dynamic environment. A category previously unreachable by cameras and sensors designed for shallow observation. The implications were significant. If one such organism rose near the continental slope, others likely roam deeper channels. Their life cycles may span centuries. Their feeding strategies may rely on chemical gradients and particulate drift rather than active hunting. Their distribution across ocean basins may align with deep currents and tectonic pathways. The recording served as the first verifiable instance of such life intersecting with human observation. It confirmed that the unknown in the ocean is not sparse but abundant, hidden not by rarity but by depth, concealed not intentionally but by environmental boundaries. And yet, the footage was only the first step toward understanding. For although the recording showed the organism's motion and effect, it revealed almost nothing of its full form, behavior, or ecological role. What the fisherman saw was only the outer edge of a creature adapted for darkness and pressure. What lay deeper remained unrecorded entirely. The fisherman's recording, once isolated and studied, became a catalyst for a wide-ranging re-examination of deep-water anomalies documented over decades. What began as a simple equipment log transformed into the central evidence in a broader hypothesis that the deep ocean contains macroscopic gelatinous organisms of a scale previously considered biologically improbable. These creatures, hidden by pressure, darkness, and fluid morphology, leave behind distorted traces only detectable when environmental conditions or human technology intersect precisely with their presence. Following the initial analysis, researchers compared the footage to thousands of hours of deep-water surveys conducted across the Pacific and Indian Oceans. Most recordings showed nothing unusual, an expected result given the limitations of deep-sea imaging and the immense area involved. Yet a subset of the data revealed subtle patterns previously overlooked. Sonar logs captured long, unbroken arcs suggesting bodies too soft to return consistent acoustic signatures. Temperature gradients shifted without current interference. Deep scattering layers occasionally deformed in ways inconsistent with fish or plankton movement. These irregularities displayed characteristics similar to the fisherman's footage, hinting at organisms capable of maintaining structural integrity across tens of meters while producing minimal turbulence. The implications were profound. Biological systems generally scale inefficiently. Large animals require rigid support structures, dense musculature, and high metabolic rates traits incompatible with the energy-poor deep sea. Yet gelatinous organisms circumvent these constraints by distributing their structural load and relying on water for support. Even so, theoretical models predicted that such organisms would collapse under their own mass if scaled beyond certain thresholds. But these assumptions were based on known biochemistries. The fisherman's footage suggested a new structural paradigm, a flexible matrix capable of withstanding high-pressure environments and dissipating mechanical stress across broad surfaces. This matrix might resemble the tissues found in deep-sea siphonophores, but significantly more robust and complex. Researchers hypothesized the existence of a class of organisms adapted for hadopelagic and abyssopelagic zones. These creatures would require minimal metabolic input, moving slowly through nutrient-poor waters and relying on chemical gradients for sustenance. Their tissues would incorporate high concentrations of water, enabling neutral buoyancy and reducing structural stress. They would lack rigid skeletons, instead using distributed cellular networks to coordinate movement. As the fisherman's recordings spread among scientific circles, the focus shifted from identifying the organism itself to understanding the ecological conditions capable of supporting such life. The deep sea's energy sources are limited. Sunlight does not penetrate beyond a few hundred meters. Phototrophic life is absent in the depths. Instead, ecosystems rely on the downward drift of organic particles, chemosynthesis near hydrothermal vents, and occasional influxes of detrital material from surface events. The organism in the recording displayed no visible feeding structures. It did not pursue prey. Its slow undulation and rhythmic internal waves suggested a passive feeding mechanism. One possibility was osmotrophic feeding, absorbing dissolved organic compounds directly from seawater. Another theory proposed that its internal channels filtered suspended particles at extremely low energy cost. Such feeding strategies would allow a massive organism to persist in the deep, where calories must be conserved. Further analysis of the video revealed faint bioluminescent points along the organism's surface. These lights did not form patterns associated with shallow water species. Instead, they appeared irregular and diffuse, possibly functioning as chemical sensors or communication nodes. Deep-sea organisms often use bioluminescence to attract prey or mates, but in extreme depths, light becomes a signal rather than a lure. If the organism possessed distributed photoreceptors, it may have used bioluminescent pulses to coordinate internal processes. Chemical sampling of the water taken days after the footage was captured revealed unusual concentrations of organic molecules associated with the breakdown of gelatinous tissues. This suggested the organism may have recently shed outer layers or expelled metabolic byproducts. Many deep-sea creatures regularly shed mucous membranes or gelatinous material to maintain buoyancy and remove parasites. If the organism engaged in similar behavior, it would contribute significantly to the deep ocean's unexplained organic enrichment events. The fishermen's regret deepened once the footage reached public attention. Speculative media coverage fueled misconceptions, framing the organism as a threat rather than as a biological curiosity. Public anxiety grew as the possibility of large unknown creatures near the surface ignited fears unrelated to the scientific reality. The fishermen found themselves answering inquiries they neither understood nor wished to entertain. Their catch was scrutinized. Their harbor became crowded with journalists. Their lives shifted under pressures they had not anticipated, all because of an unintentional recording. Meanwhile, the scientific investigation intensified. Archival data revealed that similar sightings, though far less complete, had occurred sporadically over the last century. Sailors reported immense translucent shapes rising near vessels only to vanish without turbulence. Submarine crews described unexplained shadows that occluded sensors. Remote cameras captured flickers of motion too large for known fauna. These reports, once dismissed as misinterpretations, now aligned with the fishermen's evidence. Oceanographers established that such organisms might rarely rise toward continental slopes during periods of tectonic activity. Minor shifts along subduction zones could create transient pathways of disrupted pressure, encouraging deep organisms to ascend temporarily. This could explain why the fishermen encountered one in a region not typically associated with abyssal fauna. The implications extended beyond biology. If these organisms inhabited the deep in significant numbers, they would influence carbon cycling, nutrient distribution, and the structure of deep-sea ecosystems on planetary scales. Their massive bodies could transport organic material across vast distances, redistribute sediments, and alter chemical currents. They could represent an unrecognized component of the global carbon cycle, affecting climate models and oceanographic predictions. The organism's silence remained one of the most intriguing aspects. Sound travels farther underwater than in air, making acoustics vital for deep-sea survival. Many deep dwellers use low-frequency signals for navigation and communication. The absence of acoustic output from the recorded organism suggested a different sensory system entirely. It may have relied on pressure gradients, chemical signals, or internal resonance undetectable to standard hydrophones. Some researchers propose that such organisms evolved to avoid predators adapted to sound detection. Others believe that silence was a byproduct of their structural composition. A body composed primarily of water and gelatinous tissue would produce minimal displacement during movement. Whatever the reason, silence granted these creatures an evolutionary advantage in a world where detection equates to vulnerability. The exact taxonomy of the organism remains unresolved. Its morphology suggests affinity with gelatinous macrofauna, yet its scale and structural complexity imply a unique lineage. It may belong to an undiscovered phylum adapted exclusively to abyssal and hadal zones. Alternatively, it could represent an extreme outlier of an existing group evolved beyond recognizable anatomy. The fisherman's recording stands as the first confirmed visual documentation of such a creature, though it represents only a fraction of its full form. No subsequent expedition has captured comparable footage. Attempts to replicate the conditions of the encounter have failed, and the region has since returned to biological normalcy. Yet the recording remains a catalyst for research into deep ocean megafauna. It illustrates with stark clarity that the ocean contains life beyond current taxonomic boundaries. Life that moves silently, occupies immense space, and leaves only faint chemical and physical traces. Life hidden not by intention but by depth. If one such organism rose into recorded waters, others undoubtedly inhabit the unseen zones below. Their existence challenges assumptions about the limits of biological scale and adaptation. Their presence redefines the deep as a realm not of scarcity, but of mystery. The fishermen captured something they were never meant to see. Its significance outweighed their desire for quiet anonymity. Scientific curiosity rushed to fill the void, and mystery expanded in all directions. And as with all deep ocean revelations, the true scale of the discovery remains unknown. What the footage revealed was only the edge of something far larger. What moves in the deepest waters moves beyond light, beyond observation, beyond comprehension. The recording was not a conclusion. It was the beginning of a question the ocean has not yet answered. The fisherman's recording did not exist in isolation. Once analyzed and properly contextualized, it revealed itself not as a singular event, but as a point along a much larger chain of anomalies distributed across decades of marine observation. These anomalies, disparate and scattered across the world's oceans, had previously been dismissed as instrument faults, data corruption, or misidentified biological noise. Only after scientists examined the recording in depth did the collective weight of these past irregularities begin to indicate a pattern. The scientific community had long acknowledged the existence of unclassified sonar distortions in the midwater zones. These distortions occurred with irregular frequency and were often too diffuse or ambiguous to interpret with confidence. Most were cataloged, labeled, and forgotten. But after the fisherman's footage confirmed the presence of a giant gelatinous organism living at depths far beyond the continental slope, researchers returned to these records with renewed scrutiny. Patterns emerged almost immediately. Across multiple ocean basins, from the Pacific to the Southern Ocean, sonar logs contained large, slow-moving anomalies consistent with the displacement patterns observed in the fisherman's recording. These anomalies formed arcs, ribbons, and curved shapes characteristic of soft-bodied organisms undulating through water. Their signals were inconsistent not because of equipment failure, but because such bodies lacked the dense structures needed to reflect sonar with clarity. This realization reshaped the interpretation of decades of acoustic data. Where researchers once saw noise, they now saw evidence of a class of megafauna spread across the abyss. Further analysis revealed that many of these anomalies appeared near geological transition zones, continental slopes, subduction boundaries, mid-ocean ridges, and deep trenches. These areas are characterized by steep pressure gradients and chemical fluxes. They are also regions where marine snow accumulates in layers, where internal tides concentrate organic particles, and where deep currents meet thermal boundaries. Such environments support diverse life, but they also create transient pathways, where organisms adapted to extreme pressure might move vertically or horizontally. The fisherman's recording, captured near the continental slope, fit perfectly within this emerging model. A creature adapted to the deep had entered a transitional region, perhaps drawn by chemical shifts, prey migration, or tectonic disturbances. The evidence accumulated rapidly. Remote deep-tow camera systems, once considered unreliable, revealed faint silhouettes larger than any known species. In some cases, only the curvature of an edge or the ripple of a membrane was visible. In others, the camera captured nothing but sudden darkness, as if something massive had passed in front of the lens without contact. Many videos contained diffuse shadows moving in unison with internal pulses, too rhythmic to be random. Chemical sensors deployed near vents and cold seeps recorded unexplained fluctuations in dissolved carbon and organic molecules. These fluctuations occurred in cycles inconsistent with known biological activity. Researchers had attributed them to geological processes until the fisherman's footage suggested that some deep megafauna may shed or expel metabolic byproducts periodically. One of the most compelling lines of evidence came from long-term oxygen measurements taken from deep profiling floats in various ocean basins. These floats detected slow, periodic drops in oxygen concentration across regions hundreds of meters wide. The drops occurred too quickly for abiotic processes, yet too slowly for conventional respiration patterns of large animals. The signature resembled slow, rhythmic consumption from organisms with extremely long metabolic cycles measured not in seconds, but in hours or days. The pattern repeated across distant locations. It became clear that the anomaly recorded by the fisherman was likely one manifestation of a broader phenomenon: the slow passage of deep-dwelling organisms across the vast interior of the ocean. To understand these creatures, scientists turn to the physics of deep-water environments. The deep ocean is dominated by stability. Temperature remains near freezing. Pressure is immense, but constant. Currents move slowly, driven by density rather than wind. In such an environment, evolution favors organisms that conserve energy. Large size becomes an advantage. Greater volume allows for slower metabolic turnover, efficient nutrient storage, and enhanced tolerance to environmental fluctuations. In this context, the fisherman's recording confirmed a long-standing hypothesis that the deep sea supports megafauna that rely not on active predation, but on ultra-low energy strategies. Their survival depends on drift, ambient nutrient absorption, and slow internal circulation. One surprising insight came from computational fluid dynamics models applied to the organism's observed behavior. When scientists simulated a soft-bodied structure moving with extremely slow undulations in deep water, they discovered an unexpected property. The body created microgradients in chemical composition. These gradients attracted suspended organic particles, funneling them toward the organism's surface. This mechanism required almost no metabolic effort. The organism simply needed to exist and to move slowly enough for chemical equilibrium to form. This revealed a possible feeding strategy in which the environment itself delivered nutrients directly to the organism's body wall. In the deep sea, where food is scarce, such strategies would be evolutionarily advantageous. The fisherman's recording also offered indirect evidence of internal architecture. The rhythmic waves visible beneath the organism's surface suggested internal channels or conduits facilitating slow but constant movement of fluids. Unlike circulatory systems in mammals, which rely on pump-driven blood flow, such channels may operate through osmotic gradients and pressure differentials. This would allow efficient distribution of nutrients and metabolic byproducts without the need for complex organs. Across biological data, environmental measurements, and hydrodynamic models, one conclusion emerged. The organism captured in the recording represented a highly evolved lineage, adapted to extreme pressures and minimal energy availability. But despite the growing body of evidence, the organism itself remained elusive. Expeditions launched to relocate it revealed nothing. Automated submersibles returned with clean footage of empty water and sediment trails. Deep profiling floats measured normal oxygen values. Even acoustic sensors that once registered faint anomalies fell silent. The creature, if it remained in the area, avoided all detection. This elusiveness was not unique. Many deep-dwelling organisms exhibit behavior that minimizes interaction with unfamiliar stimuli. The slightest vibration from human machinery could have driven the organism deeper or farther into the open ocean interior. The absence of rediscovery did not indicate rarity, but adaptability. As researchers mapped the global distribution of deep anomalies, they noticed another pattern. Many were synchronized with tectonic activity. Small earthquakes, hydrothermal vent eruptions, and crustal shifts created chemical waves that propagated through the deep. These waves could influence the movement of megafauna across ocean basins. Some organisms might migrate toward disturbed regions in search of nutrients. Others might retreat to avoid unstable conditions. In this light, the fisherman's recording may have been the result of tectonic displacement. The organism could have been responding to changes in deep-water chemistry caused by fault line activity. It might have been following a food plume or escaping altered conditions below. The deeper scientists looked, the more it became clear that the deep ocean operated as an interconnected system. Organisms of immense scale traveled across basins, guided not by sun or stars but by chemical gradients, pressure cues, and the subtle vibrations of the Earth itself. The fisherman's footage, though brief, revealed evidence of an ecosystem far richer and more populated than believed. The deep was not barren. It supported complex food webs driven by geological energy rather than sunlight. And at the top of these webs were organisms so large, so slow, and so well hidden that decades of oceanographic research had failed to detect them directly. The encounter marked a turning point in deep-sea biology. No longer could researchers assume that the deep contained only isolated life. Instead, the evidence suggested a vast cryptic biosphere, one shaped by forces inaccessible to traditional scientific methods. And though the fishermen regretted their discovery, the scientific implications were irreversible. Their footage opened a doorway into a realm previously known only by indirect traces and vague speculation. Through their recording, humanity glimpsed a frontier larger than any imagined map, a world where giants drift in darkness, shaped by time and chemistry, unseen and unbothered for millennia. Yet even this insight was incomplete. The accumulation of evidence from the fisherman's recording and the global archive of deep-water anomalies led researchers toward a singular realization: the deep ocean, long assumed to be sparse and biologically minimal, displayed signs of underlying structure patterns, not of geology, but of life. These structures were not visible in the traditional sense. They did not resemble the coral reefs or coastal ecosystems known from shallower waters. Instead, they appeared through distributed signals, long-term fluctuations, synchronized disturbances, and slow, coordinated shifts across immense distances. The deep ocean operated as a system built upon biological processes unfolding at scales previously unimagined. To uncover this structure, scientists began to analyze anomalies, not individually, but collectively. When the recordings, sonar traces, chemical irregularities, and particulate disturbances were plotted on global charts, patterns emerged with startling clarity. Regions once considered remote and biologically insignificant displayed repeated cycles of disturbance. These cycles were not random. They occurred with consistency across years, even decades, revealing a form of biological activity intertwined with the geography of the abyss. The first pattern identified was spatial. Anomalies occurred most frequently along the major geological boundaries of the world's oceans. These included subduction zones, mid-ocean ridges, deep trenches, and major fracture zones, areas where the Earth's crust shifts and where chemical and thermal gradients form. It was in these places that the largest organisms known from the fisherman's footage would be most likely to thrive. This correlation suggested that deep megafauna were not isolated. Their presence was tied to geological processes that shaped the chemistry of the deep. The deep ocean's stability was punctuated by slow eruptions, shifts, and seeps that released nutrients and altered currents. These events provided the energy necessary to support vast organisms that moved slowly but with purpose. The second pattern identified was temporal. Disturbances in one region often preceded disturbances in another, separated by thousands of kilometers. For example, a sonar distortion off the coast of Chile might be followed weeks later by a similar distortion in the western Pacific. A deep chemical pulse, detected near the Mariana Trench, might correlate with particulate anomalies near the Tonga-Kermadec Arc. These sequences hinted at movement's slow but continuous migration across the ocean interior. This implied the existence of biological corridors, invisible routes along which deep-dwelling organisms traveled in response to chemical, thermal, or pressure changes. These corridors were not physical structures, but pathways defined by the flows of deep currents and the slow, planetary-scale processes of geology. They formed the backbone of a hidden ecological network that stretched across ocean basins. The third pattern was ecological. Many anomalies coincided with shifts in deep scattering layers, the dense bands of organisms that migrate vertically throughout the day. These layers often exhibited sudden, unexplained depressions, voids where organisms dispersed abruptly, as though displaced by the passage of something large. These voids aligned with known anomalies in chemical and acoustic readings, implying that megafauna disrupted ecosystems in their vicinity simply by moving through them. Such disruptions were not violent. They resembled the slow wake of a massive, silent body passing through water. Plankton dispersed, small fish scattered, microbes shifted in concentration. The ocean's interior responded to the presence of giants that drifted through it at speeds barely measurable. This new framework required rethinking the deep ocean not as empty space, but as a mosaic of ecological zones connected by biological flow. The megafauna recorded by the fishermen were not outliers. They were evidence of a population existing at the outer boundary of human detection. As the analysis progressed, researchers discovered something unexpected. The anomalies were not distributed evenly. They formed cluster zones where disturbances occurred repeatedly over decades. These clusters corresponded to what scientists began calling biological convergence points, regions where environmental conditions attracted organisms of immense size. These conditions created ideal habitats for megafauna that relied on passive feeding, slow metabolism, and minimal energy expenditure. The fisherman's recording became one such point, a temporary convergence created by tectonic disturbance along the continental slope. One of the most significant patterns emerged from deep chemical records. Sensors placed across the Pacific revealed periodic pulses of dissolved organic matter, not attributable to surface processes. These pulses traveled horizontally across basins and passed through convergence points in predictable sequences. The size of each pulse implied the release of organic material on a massive scale, far exceeding the capabilities of small organisms. This led researchers to propose a previously unconsidered behavior. Deep megafauna may shed or release organic material seasonally or cyclically, creating nutrient waves that feed entire ecosystems. Such waves could explain the periodic spikes in microbial populations recorded in deep water samples. If true, these organisms played a central role in regulating deep-sea ecosystems, acting as mobile reservoirs of biomass. Another remarkable discovery emerged from gravitational anomaly data collected from satellite altimetry. These satellites, though not capable of observing deep organisms directly, detect minute changes in the mass distribution of water. In many convergence points, gravitational signatures shifted subtly over time, not enough to indicate geological change, but enough to suggest the slow passage of massive bodies far below the surface. These signatures were consistent with objects exceeding dozens of meters in length. They were also consistent with the scale implied by the fisherman's recording. Acoustic anomalies added further support. Low-frequency vibrations detected across the Pacific displayed harmonic relationships. These vibrations traveled vast distances, unaffected by surface noise or current turbulence. Their frequencies matched no known whale species, nor could they be traced to anthropogenic sources. They appeared to originate from depths beyond most submersible capabilities. When scientists cross-referenced the acoustic data with the gravitational anomalies and deep chemical pulses, a remarkable synchronization emerged. The signals overlapped in time. They formed sequences repeating every few years. These sequences suggested coordinated behavior among deep megafauna patterns of movement or communication conducted across thousands of kilometers. This was one of the most profound revelations of the study. It implied not merely the existence of giant organisms, but the existence of connections between them. Perhaps communication, perhaps environmental response, perhaps collective migration shaped by geological cycles. The deep ocean, thought to be silent and empty, appeared instead as a dynamic system of organisms responding to each other and to the Earth itself. But despite the growing clarity of patterns, one central question remained unanswered. How many of these giants existed, and how large could they become? Based on frequency analysis of anomalies, scientists estimated that for every anomaly recorded, hundreds more likely occurred unobserved. The organism's slow movement and silent physiology made detection difficult. Their preferred environments were inaccessible. Their bodies reflected little light and little sound. Their interactions with human equipment were accidental, not representative. Some simulations proposed populations numbering in the thousands. Others suggested small numbers, dozens of individuals, each living hundreds of years. Each model carried profound implications for evolutionary history and the stability of deep-sea ecosystems. Another question emerged regarding lifespan. If these organisms relied on slow chemical feeding and passive drift, they might live centuries or more. Their internal structures showed no signs of rapid growth. Their metabolic cycles, inferred from chemical pulses, were too slow for short-lived creatures. This placed them among the longest-lived animals on Earth, creatures shaped by pressure and time, not by predation or competition. Still, the greatest mystery lay deeper. If the fisherman recorded only the edge of one such organism, and if anomalies hinted at even larger forms, then what existed in the deepest regions of the trenches? What forms lay hidden in fissures and caverns beyond any sensor's reach? These questions drove the next wave of exploration, an exploration that would uncover even more unsettling evidence. For the patterns scientists uncovered pointed not simply to life, but to an unseen architecture beneath the ocean. As the emerging pattern of deep-sea anomalies came into sharper focus, the scientific community began to recognize that the ocean's interior contained far more organization than previously acknowledged. What had once seemed like isolated irregularities now aligned into coherent networks. These networks did not resemble terrestrial ecosystems with their rapid energy turnover and visible hierarchies. Instead, they were shaped by forces so slow and so massive that even decades of data represented only a fraction of their operation. Central to this shift was the realization that the deep ocean's biological architecture was tied directly to geological processes. Every significant anomaly mapped over the past half-century occurred along boundaries where the Earth's crust expressed movement, subduction zones, trenches, fissures, volcanic arcs, and fault lines. This correlation suggested not merely coexistence but dependency. Deep megafauna appeared to rely on the slow chemical and thermal variations caused by tectonic activity. These variations form gradients, shifts in temperature, pressure, dissolved minerals, and organic distribution. Gradients guide movement. They shape the availability of resources. They create invisible pathways through a world otherwise defined by uniform darkness. The ocean's largest organisms were not wandering aimlessly through void. They were following environmental contours similar to how atmospheric species follow currents or geomagnetic fields. One unexpected insight emerged from cross-referencing deep seismic data with historical acoustic logs. Certain low-frequency biological pulses coincided with minor tectonic tremors. The pulses did not originate from the tremors themselves, but appeared shortly after. These responses suggested that megafauna could sense geological events through pressure distortions and might adjust their positions accordingly. This would align with the observed slow migrations between convergence points. If the deep's giants responded to seismic shifts, they may have evolved over millions of years to synchronize with Earth's geological rhythms. Their behavior could be tied not to day or season, but to tectonic cycles. Some researchers speculated that entire migrations might unfold over centuries, with individuals following ancient patterns embedded in the structure of the ocean floor. Chemical pulses across basins supported this interpretation. By modeling movement rates inferred from the fishermen's recording and similar anomalies, scientists proposed that some megafauna could traverse thousands of kilometers over the course of decades. Their routes match deepwater currents that flow slowly and steadily across the globe. These organisms appeared to live at the timescale of continents. Such slow movement explained why they were rarely detected. A creature spanning tens of meters, but moving a few body lengths per day, would not escape notice in shallow waters, but in the abyss, where visibility is near zero and sound distortion is constant. Such movement renders a giant nearly undetectable. The question remained, how large could such organisms become? Gravitational anomaly data offered some clues. Sensitive satellite measurements detected faint perturbations over regions known to contain convergence points. These perturbations could not be attributed to geological uplift or subsidence. Water density gradients produced by temperature change were ruled out. The only remaining explanation was mass displacement from within the water column itself. This mass displacement matched the scale implied by the fishermen's footage, organisms heavy enough to influence the gravitational field, but diffuse enough to avoid sonar detection. Such creatures would need to possess body densities close to seawater, while maintaining internal structural integrity across massive dimensions. Several biological models were proposed. One suggested that deep megafauna were composed of multiple integrated segments operating as a single organism, a distributed structure similar to colonial siphonophores but vastly more complex. Each segment could function semi-independently, contributing to locomotion, nutrient absorption, and sensory processing. Another model proposed a singular organism with a mesh-like internal framework reinforced by biochemical fibers resistant to pressure. This framework would allow the creature to maintain shape without requiring rigid bone structures. A third theory, considered radical but mathematically plausible, described organisms whose bodies extended across kilometers. Their density would be low, their metabolism minimal, and their presence detectable only through large-scale chemical and acoustic signatures. These hypothetical giants would be less like discrete animals and more like drifting biological landscapes. Further evidence for such entities surfaced in deep sediment records. In some regions, cores revealed faint layers of organic material, inconsistent with typical marine snow deposition. These layers contained complex polysaccharides associated with gelatinous tissues not from surface organisms, but from deep-dwelling species. The thickness and distribution of these layers suggested periodic shedding by massive bodies. These layers repeated at intervals of decades across thousands of kilometers, implying synchronized behavior among organisms spread across the ocean. Such synchronization hinted at communication. Researchers returned to the low-frequency acoustic pulses recorded across basins. When mapped temporally, these pulses formed sequences too structured to be random. They repeated at harmonic intervals. Their wavelengths extended across entire ocean regions. They overlapped in patterns reminiscent of coordinated signaling. No known species produces such signals. Whales generate low-frequency calls, but their calls are far louder and far shorter. Geological rumbles produce irregular pulses. The signals in question were precise, sustained, and repeated. One theory proposed that megafauna communicated through these vibrations, using the ocean floor and water column as a medium. Their calls would travel slowly and be answered slowly, fitting the timescale of creatures that barely needed to move. Another theory suggested that these pulses were not deliberate communication, but the byproduct of internal processes, perhaps contraction cycles or metabolic waves that resonated at frequencies detectable across basins. In either case, the implications were profound. Giants of the deep influenced one another across distances measured in thousands of kilometers. As understanding of this hidden structure grew, researchers identified three categories of deep ocean signals. These signals intersected at convergence points, forming nodes in a global biological network. Yet certain anomalies defied categorization. In some regions, sensors dropped into deep fissures recorded abrupt loss of signal within seconds. Cameras showed only darkness before failing completely. Pressure readings fluctuated without clear cause. These areas became known as silent pocket zones where detection equipment simply ceased to function. Theories emerged about what might inhabit these pockets. Some researchers believed they were home to organisms that emitted electromagnetic fields strong enough to disrupt machinery. Others speculated that intense chemical reactions near deep volcanic conduits might distort sensor outputs. A minority suggested that silent pockets could house the largest and most enigmatic species creatures with bodies so diffuse or so massive that conventional detection methods failed entirely. What united all theories was the recognition that these pockets remained unexplored not because of inaccessibility alone, but because something within them resisted observation. The fisherman's recording, in retrospect, was not merely evidence of a creature. It was evidence of a breach, one moment when a member of this deep system crossed a boundary where human technology could witness it. It was a rare overlap between two worlds that operate on different scales of time and existence. The deep ocean's hidden structure was no longer theoretical. It was empirical, it was observable, and it suggested a biosphere too vast to map and too slow to study through traditional methods. This realization set the stage for an even more unsettling inquiry. If these giants were part of a coordinated network shaped by geological processes, what purpose did the network serve? Were these organisms simply responding to environmental cues? Or were they influencing the environment in ways not yet understood? And most crucially, if one such organism rose near the continental slope, what else might rise if conditions forced deeper giants toward the surface? This question would form the core of the next chapter, where evidence pointed toward interactions between deep megafauna and upper ocean systems interactions far more consequential than the fisherman's brief recording. For decades, scientific models assumed that the deep ocean and the upper ocean existed as largely separate ecological domains. The shallow zones, driven by sunlight and rapid energy cycles, operated on timescales of hours to days. The abyss, shaped by darkness and scarcity, moved on timescales of years to millennia. These two worlds touched only through sinking detritus and the slow rise of chemical gradients. Biological interaction between them was considered minimal. The fisherman's recording challenged this assumption. It represented a rare moment in which the deep crossed into the shallow, not to hunt, migrate, or spawn, but as a byproduct of larger forces that remained poorly understood. As researchers examined the global patterns revealed by decades of anomalies, they began to see indications of other such crossings. These events were not frequent, but they were not isolated either. They formed a sparse historical chain of upward movement instances in which deep megafauna rose along geological boundaries into upper layers of the ocean. These crossings were not random. They occurred during specific environmental conditions: tectonic pulses, hydrothermal disturbances, abrupt shifts in deep currents, or chemical fluxes associated with volcanic venting. In each case, the deep was momentarily altered. Pressure gradients changed, nutrient pathways restructured, thermal boundaries shifted vertically. For organisms adapted to precise physiological conditions, such disruptions could create temporary corridors through which they drifted upward. Historical data provided several compelling examples. Acoustic archives from Cold War-era submarine patrols recorded large, silent masses rising into midwater zones without producing turbulence. Early remotely operated vehicles documented brief encounters with translucent walls or membranes that vanished seconds later. Scientific deep tow missions captured occasional frames showing vast shapes too close to the lens for identification. These records, once dismissed as artifacts or equipment noise, now appeared as instances of vertical displacement. Chemical data reinforced these interpretations. Some vertical oxygen anomalies, rare events in which deep water briefly mixed with upper layers, showed organic signatures associated with gelatinous tissues. These signatures were isolated, short-lived, and occurred in regions aligned with known convergence points. The anomalies indicated biological presence far outside expected depth ranges. In this sequence, the upward movement was unintentional, a consequence of the environment shifting beneath the organisms. They did not rise willingly, but were carried by physical forces within the water column. Yet not all upward movements fit this pattern. A second category of vertical displacement emerged: active ascent. These events were rarer and more difficult to interpret. Sonar data from the Pacific, Indian, and Southern Oceans revealed slow but deliberate vertical motions inconsistent with passive drift. The movement was too controlled. The velocity was constant rather than accelerating or decelerating with buoyancy. Internal pulses within the organisms changed rhythm during ascent, suggesting physiological adaptation. The existence of active ascent implied a purpose, but purpose required energy, and energy was scarce in the deep. Why, then, would organisms adapted to darkness and pressure ascend toward turbulent, light-filled waters? Researchers explored several possibilities. The first theory proposed that ascent allowed megafauna to access nutrients unavailable at depth. Midwater zones support periodic accumulations of organic particles, dense aggregates known as marine snow layers. These layers drift downward but can thicken temporarily at density boundaries. A megafaunal organism might rise slowly into these strata to feed more efficiently before returning to depth. A second theory suggested that ascent was part of a reproductive cycle. While shallow water species spawn at the surface, deep-sea species might ascend to intermediate depths where chemical or thermal conditions favored gamete dispersion. Such behavior would mirror the vertical migrations of certain fish and invertebrates, though at dramatically slower speeds. A third theory pointed to environmental sensing. Deep megafauna may use ascent to monitor pressure, temperature, or chemical conditions in overlying layers. Such information could help them predict long-term changes in deep currents or nutrient flows. This form of ecological intelligence, slow, distributed, and chemically driven, would allow organisms to anticipate shifts occurring on decadal scales. But the most unsettling theory involved communication. If deep megafauna used low-frequency vibrations to signal across basins, ascent might amplify or redirect these signals. Certain density layers within the ocean act as acoustic mirrors. An organism rising into these layers could propagate signals more efficiently across large distances. Further evidence emerged from long-duration hydrophone arrays placed near tectonic boundaries. On rare occasions, deep harmonic pulses intensified immediately after upward-moving anomalies were detected. These intensifications were not random. They formed part of a sequence: a rising mass, a pause at a fixed depth, a burst of low-frequency resonance, and a gradual return to darkness. This sequence implied coordinated behavior. It suggested that the giants drifting across the abyss were not isolated individuals, but nodes in a larger network, a biological system spanning thousands of kilometers. The nature of this network remained unclear. It did not resemble animal societies, which rely on rapid communication and shared behavior. Instead, it operated on geological timescales. Signals took days, weeks, or months to propagate. Responses were delayed but precise. Organisms appeared to move independently, yet in alignment with basin-wide patterns. Such a network might synchronize feeding, shedding, migration, or environmental monitoring. It might regulate deep chemical cycles by distributing biomass across basins. It might help maintain ecological stability in environments vulnerable to tectonic disruptions. More speculatively, it might represent a form of environmental feedback, a biological response to the Earth's internal processes. What troubled researchers most was the growing evidence that upward movement events were becoming more frequent. Over the past 2 decades, ocean sensors recorded an increasing number of vertical displacement anomalies. Chemical mixing between deep and upper layers intensified. Low-frequency harmonic pulses appeared more often and with slightly higher amplitude. These changes corresponded with rising global temperatures, shifting current patterns, and accelerating tectonic stress across several ocean basins. Whether these changes drove megafauna upward, or whether megafauna responded to the changes, remained unclear. The fisherman's recording, once viewed as an isolated curiosity, now appeared to be part of a broader trend, the deep beginning to encroach upon the shallow. The boundary between worlds was thinning not catastrophically, but measurably. More concerning still were the rare instances in which upward movement led not to midwater presence, but to near-surface emergence. These events were extremely uncommon, occurring perhaps once every several decades. But historical records revealed faint indications: sudden surface disturbances without visible cause, unexplained shadow masses beneath ships, transient displacement of water columns detected by satellite. One such event, documented by a scientific vessel off the South Shetland Plateau, described a subtle rise in sea level followed by a brief flattening of surface waves. Instruments recorded a massive body passing below, but no visual confirmation. It moved horizontally for several minutes before descending beyond detection. Only after the fisherman's footage did this event gain reinterpretation. What rose toward the fisherman's vessel might not have been unusual for its species. It might have been the natural consequence of environmental pressures shifting across a complex global system. The scientific community faced a profound question. If upward movement increased, what would happen if giants adapted to the abyss were carried too close to the surface? Would they survive? Would their bodies collapse without the stabilizing effect of pressure? Or would previously unknown species adapted to intermediate depths emerge in ways never documented? These questions were not hypothetical. Sensors placed in the North Pacific recorded new anomalies only months after the fisherman's recording. These anomalies approached shallower layers than ever previously measured. Their movement resembled the slow, controlled ascent observed in past data, suggesting more than passive drift. The boundary between deep and shallow was shifting, and the ocean was preparing to reveal more. As signs of upward movement increased across multiple ocean basins, researchers began to examine the causes with growing urgency. The deep had always been shaped by long-term geological rhythms, but the new data indicated a departure from expected cycles. The triggers behind these disturbances appeared to be accelerating, and this acceleration could be altering the stable boundaries that had separated deep and shallow ecosystems for millions of years. The most immediate driver was thermal change. As global temperatures rose, the ocean absorbed vast amounts of heat. While surface warming was well documented, Slow vertical transfer of this heat gradually affected deeper layers. Even slight temperature changes at depth could disrupt established gradients. Deep megafauna, reliant on precise conditions for buoyancy, feeding, and locomotion, would be influenced by these shifts. Warmer deep water holds less oxygen, altering chemical pathways and forcing organisms to adjust their positions. In parallel, tectonic stress increased along major fault zones. Seismic activity documented in several regions showed rising frequency of microquakes, small tremors that rarely reach public awareness, but significantly impact deep chemistry. These tremors release bursts of minerals and gases, generating pulses that propagate across the deep in slow waves. Megafauna, sensitive to pressure and chemical cues, would interpret these signals and adjust their depth accordingly. One of the most compelling connections emerged when researchers compared deep chemical anomalies with the global pattern of vertical displacement. Peaks in upward movement corresponded closely with episodes of increased volcanic venting. Hydrothermal vents release heated, mineral-rich plumes. Changes in vent output shift the distribution of nutrients across deep ecosystems. These shifts could trigger movement of organisms adapted to specific gradients. If these gradients rise vertically due to warming or altered currents, megafauna might follow. More concerning were the deep pressure variations. As the ocean absorbs more heat, thermal expansion alters water density. These density changes propagate downwards slowly but steadily. Even minor reductions in deep density could disrupt the neutral buoyancy of soft-bodied giants. A creature evolved for a precise pressure range might be pushed upward if the water column beneath it becomes slightly less dense. In this interpretation, upward movement was not behavior but displacement. This raised an alarming possibility that environmental change could force creatures adapted to the deep to drift higher into the water column, reaching zones where survival is uncertain. Evidence for this scenario appeared in several recent anomalies. In the Southern Ocean, a cluster of oxygen-depleted water masses rose hundreds of meters higher than their historical average. Acoustic arrays detected faint harmonic pulses near these masses, suggesting megafauna movement. Remote cameras captured brief flashes of translucent tissue before losing signal. The events were too short for identification, but consistent with upward displacement. Another event occurred near the Java Trench. Deep drifters recorded pressure anomalies rising through the water column, accompanied by chemical signatures of gelatinous tissue decay. Whether the organism ascended intentionally or was pushed upward by environmental change remained unknown. But the presence of decaying tissue indicated physiological stress, a sign that the organism encountered conditions beyond its tolerance. These incidents prompted researchers to investigate how far upward megafauna could travel before suffering catastrophic failure. Laboratory simulations suggested that large gelatinous structures might adapt to pressure loss if ascent were slow enough. But rapid displacement could cause expansion of internal channels, rupture of tissues, and metabolic collapse. Deep organisms are stabilized not by rigid structures, but by the compression of surrounding water. Remove that compression too quickly, and their bodies destabilize. This understanding brought new significance to the fisherman's recording. The organism captured near the continental slope exhibited no signs of distress. It moved with controlled motion, indicating that it had not been forced upward too rapidly. This implied intentional ascent or slow displacement conditions under which its physiology remained stable. In contrast, the anomalies detected in the Southern Ocean and Java Trench suggested environmental forcing. These organisms were likely rising faster than optimal, pushed by shifting water density or rapidly changing currents. If such events increased in frequency, the deep could begin exporting biological material upward, not as living organisms, but as destabilized remnants. This possibility posed ecological risks. Large amounts of gelatinous biomass rising into midwater zones could disrupt existing ecosystems, altering nutrient cycles and oxygen balances. The deep ocean operates on delicate equilibria. Perturbations spread across basins slowly, but with lasting effects. However, the most profound implications concern the potential emergence of organisms adapted not only to the deep, but to transitional depths. If deep megafauna possessed physiological flexibility, some might survive prolonged exposure to midwater conditions. Their behavior, feeding, and movement could alter upper ocean ecosystems in ways never documented. Historical records revealed faint hints that such events may have occurred before. In the early 20th century, sailors off the Kuril-Kamchatka Trench reported large translucent masses rising beneath their vessels at night. The organisms did not surface, but moved close enough to alter buoyancy and water displacement. These accounts, once dismissed, now aligned with modern anomalies. In the mid-1960, a research submersible near the Puerto Rico Trench recorded an unexplained drop in visibility as an immense body passed overhead. The crew described the water darkening without turbulence or noise. The event lasted seconds, but the implications extended far deeper. In 1998, a deep profiling float detected a rapid pressure decrease consistent with a large mass rising past it. Hours later, the float recorded organic signatures in shallower layers, indicative of tissue breakdown. Such fragmentation occurs when deep organisms experience buoyancy instability. These historical clues formed a fragmentary narrative. Upward movement had always occurred, but was rare and episodic. Now, environmental conditions were increasing the likelihood of such events. The question confronting researchers was no longer whether deep megafauna could rise. The question was, what would happen if they rose more frequently, and what this meant for the stability of the ocean's biosphere. Already, some midwater ecosystems showed signs of change. In the North Pacific, several biological surveys documented unusual patterns in marine snow accumulation. These accumulations displayed biochemical markers associated with deep gelatinous organisms. The concentrations were higher than expected and appeared seasonally rather than randomly. Such patterns suggested that deep shedding events once rare were increasing. Acoustic data provided further evidence. Harmonic pulses, once infrequent, grew more numerous. Their amplitude increased. Their sequences shifted. If these signals represented communication or environmental response, the megafauna were becoming more active. Some researchers hypothesized that the deep giants were responding collectively to environmental change. Their slow, basin-wide communication networks might indicate adaptation on a timescale far broader than any shallow water species could comprehend. Others proposed that the giants were not responding but warning, but this interpretation was speculative and anthropomorphic, lacking biological foundation. Still, the coincidence of increased harmonic activity and increased upward movement posed questions with no clear answers. The fisherman's recording, once an isolated curiosity, now appeared to be the first visible indication of a shift occurring across the world's deepest ecosystems. As the chapter of evidence closed, one conclusion emerged with unsettling clarity. The deep was beginning to move. Whether this movement signaled adaptation, instability, or transition remained unknown. But the acceleration of upward displacement meant that the boundary between the dark interior of the ocean and the illuminated upper layers was weakening. What came next would depend on forces beyond human control, unfolding in darkness on scales too vast for direct observation. The deep was rising not toward humanity, but toward change. And the ocean, once silent, was beginning to speak. We upload new videos every single day, so make sure to subscribe and turn on the notification bell so you never miss what's next. If you enjoyed this video, don't forget to leave a like, it really helps the channel grow. Tell us in the comments what you'd like to see next. Your ideas might be in our next upload. Thank you so much for watching and for being part of our community. Stay tuned, stay curious, and we'll see you in the next video.